Hello everybody, let us talk about the second law of thermodynamics. In my previous lecture I talked about the first law of thermodynamics, that is Q. If you supply the Q amount of heat energy to the system, certain amount of heat energy is utilized to do the work and the rest amount of energy is utilized to change the internal energy. This is the first law of thermodynamics. But the first law of thermodynamics is silent about the direction of heat flow. The first law of thermodynamics, it does not give you any direction of the heat energy. It is silent about the direction of heat energy. We don't know the direction of the heat energy if you just do the first law of thermodynamics. So we have a second law of thermodynamics. Okay, it is really simple. Second law of thermodynamics, second law of thermodynamics. Okay, so what is second law of thermodynamics? What is the statement? It is very simple. I think we talk about it in the chapter heat and temperature chapter also. The heat energy always flow from hot object to cold object. That means from high temperature to low temperature. It is impossible to extract the heat energy from cold object and throw it to the hot object. That means heat energy cannot flow from cold object to hot object. Heat energy always flow from hot object to cold object. Okay, heat energy always flow from hot object, that is high temperature, to cold object. Okay, it is impossible to extract heat energy from cold object and throw it to the hot object. It is not possible. We cannot extract, we cannot pull the heat energy from the cold object and throw it to the hot object. Let us suppose I am let's say here I have a cold object and I have a hot object here. The heat energy cannot go from this object to this object, from hot object to cold object. Naturally, heat energy, it cannot flow from cold object to hot object spontaneously. That is the second law of thermodynamics. Or simply you can say that heat energy cannot flow from low temperature to high temperature naturally, spontaneously. You can think about like your refrigerator, your air conditioning, that is not the natural process. You use some power there, that is totally different story there. Okay, so the second law of thermodynamics gives you the direction of heat energy. So what is the direction then? From hot object to cold object, high temperature to low temperature. But don't confuse, it is not the vector quantity, it is the energy. Energy is always the scalar quantity. Simply we give the direction like simply the flow of energy direction. So hot object to cold object. So this is the second law of thermodynamics, and under this law we have to talk about the heat engine. So heat engine. So what is heat engine then? Simply heat engine convert the heat energy into the mechanical work. Heat engine converts heat energy into the mechanical work. Like a steam engine. I think long time ago, the train also used the heat energy to, as a fuel. Okay, so the heat engine, it converts the heat energy into the mechanical work. That is what we call the heat engine. And the heat engine, it has basically three parts. Okay, the heat engine, it has a three component. What are they? The heat engine has a three components. So what are they? Okay, let me draw like this. So heat engine has, here you have hot source that has a high temperature. Here you have, this is the engine, and there is, here you have the heat engine has, we call cold object, we simply call cold reservoir. Cold reservoir, or people they also call sink. They also call sink. So how it works is, from here, this is the engine, you keep your working substance here. Okay, you pull the heat energy from there. Let me write down Q8 here. This is Q8. The engine absorbs the heat energy from the hot source, and here the engine does some work here. This is the W, work done output. Okay, so hot source and engine does some work, W, and if we take, like for example, from hot source, if we take 1000 joule heat energy, it cannot convert all 1000 joule heat energy into the work done. No, it is not possible. For example, let us suppose only 400 joule work is done there. Engine absorbs 1000 joule heat energy, but it does only 400 joule work. So now the 600 joule energy, it throws to the cold reservoir. We can write down QC, cold, C for cold, or you can write down QH and QL also. L means low. Okay, so look, you can think like that. Consider I am the engine. Okay, I am the engine. On this side there is a hot source. On this side there is a cold reservoir. And what I will do, I am the engine. I absorb the heat energy from the hot source. I convert the certain amount of heat energy into the useful work this way. I do some work this way. Okay, so I absorb 1000 joule energy from here. I do the 400 joule work here, useful work. Okay, and the rest 600 joule energy I throw to the cold reservoir. That's it. Okay, so this is how the heat engine work. Three components. Okay, hot source, high temperature here. If you want to write down the temperature, it is, you can write down T8 degrees Celsius, high temperature, and here T cold degrees Celsius. Okay, and here is the engine. So hot source at high temperature, you keep this at a high temperature, and cold reservoir, you keep this at low temperature. Okay, and the amount of work done here. So this is the heat engine, and here the important thing is we need to calculate the efficiency of the heat engine. So what is the efficiency of the heat engine? That is important. And what is efficiency then? The efficiency, very basic definition is efficiency, you can write down E. Efficiency is, think about it, what is the efficiency? Any idea? Efficiency is simply output divided by input. Okay, output divided by input. Now look at this. In this case, your efficiency E, what is the output here? Output is W, work done. This is the useful work, and this is our output. W divided by input. What is the input? you absorb the energy, QH amount of energy. This is the input. So W divided by QH. So this is the efficiency. This is the efficiency. But look, efficiency W. Look here, this 400 joule. How do you get this 400 joule? Look, W is equal to QH minus QC. What is QH? 1000 joule. What is QC? Here, this QC is 600 joule, okay? It is 600 joule. 600 joule. So this is 400 joule then. So work done is 400 joules. Actually, work done is QH minus QC. Okay, so efficiency W divided by QH, work done divided by input, and this is work done is QH minus QC divided by QH. If you simplify this, you get 1 minus QC divided by QH. This is the efficiency. 1 minus QC divided by QH. If you want to calculate in percentage, like a percentage efficiency, you have to multiply this by 100. Then it converted in percentage like this. So this is the formula to calculate the efficiency of heat engine. If you know the QC and if you know the QH, you can use this formula to calculate the efficiency. But normally, if the QC and QH is given, you can use this formula. But normally the temperature is given. The temperature, this temperature is given. For example, 400 degrees Celsius. Okay, this temperature TC, let us suppose this is 100 degrees Celsius. So your heat engine is working in between 400 degrees Celsius and 100 degrees Celsius. 400 degrees Celsius hot source, 100 degrees Celsius cold reservoir. So what is the efficiency of the engine? Simply people, they ask like this. So you know that the Q, this is the heat energy, but we can write down the efficiency in terms of temperature also. So if you want to write down the efficiency of the heat engine, your efficiency of heat engine, this is equal to 1 minus, look here you have a QC over QH, heat energy and temperature, they are proportional to each other. So you can write down 1 over TC divided by TH. And if you want the percentage, you have to multiply this by 100, then you get percentage here. So 1 minus TC divided by TH. So what is TC? TC, cold temperature or low temperature. Okay, cold temperature, or you can say low temperature. Low temperature. But this temperature must be in Kelvin. Okay, TC and TH both, it must be in Kelvin. Kelvin. You have to convert the degree Celsius into Kelvin. And TH, this is hot temperature, and you can say high temperature, whatever you call high temperature. Of course, this is also in Kelvin. In Kelvin, both must be in Kelvin. Okay. So please write down these two formula. Okay. The formula to calculate the efficiency of the engine is efficiency of the engine, heat engine is 1 minus QC divided by QH times 100%. This is in terms of energy, or if you want to write down the temperature, in terms of temperature, this is 1 minus TC divided by TH times 100%. So these are the formula to calculate the efficiency of the heat engine, and you know that the efficiency of heat engine is never 100%. Okay, never 100%. Maximum you can get like 50%, 55% like that due to the friction. Okay, so let me give you one sample problem how to use this formula. I have here problem what is the maximum theoretical efficiency. What is the maximum theoretical efficiency possible for an engine operating between 100 degrees Celsius and 400 degrees Celsius. Okay, so you can see this kind of problem in the exam also. So what is the maximum theoretical efficiency possible for an engine operating in between 100 degrees Celsius and 400 degrees Celsius? Of course, this is in terms of temperature, then temperature is given. So look at this, your high temperature TH, this is equal to 400 degrees Celsius. But I told you that the degrees Celsius, you have to convert this into the Kelvin. So you know how to convert the Celsius into Kelvin. 400 plus you have to add 273, right? 273, so it is now in Kelvin. This is in Kelvin. Okay, so this is 673 Kelvin, high temperature. And low temperature, this is 100 degrees Celsius, 100 degrees Celsius, and this is 100 plus 273 Kelvin. So this is 373 Kelvin. Now, what is the efficiency? The efficiency formula is, I want in percentage, so efficiency is 1 minus Tc divided by Th and multiply this by 100, you get in percentage. Okay, so this is, now plug the number, this is 1 minus Tc is 373 Kelvin, Th is 673 Kelvin, and you have to multiply this by 100%, and this is equal to, now please use your calculator. I don't have a calculator here. Let me see if I have the answer here. You are supposed to get about, roughly, okay, please do it, about 45%. Simple. Okay, so if you know the high temperature, if you know the low temperature, you can calculate the efficiency of the heat engine. Don't forget, your temperature must be in Kelvin. This is how we set the equation. So this is the second law of thermodynamics. Okay, very simple. Okay, so the chapter 18 thermodynamics, what you need to do is, let me simply remind you. You define what is thermodynamics, then you have to learn about the first law of thermodynamics. First law of thermodynamics, under these you have to do there are different thermodynamic process. Please do this isothermal process. This is temperature constant. The process carried out at constant temperature, that is called as the isothermal process. Another one is adiabatic process. Heat energy constant here, so you can say that the process carried out at constant heat energy, that is adiabatic process. Okay, you have other one is isobaric process. This is the process carried out at constant pressure, okay, and you have another one, constant volume, we call isovolumetric, or you can call isochoric process also. Isochoric process at constant volume, the process carried out at constant volume. So you have a 4 thermodynamic processes, okay, and you know that if you have a cylinder and there is a piston, okay, then if you supply the Q amount of energy to the system, then what happens? This Q amount of energy, Q, it is utilized to do the work and to change the internal energy, okay. So this is the first law of thermodynamics. Now look at this. If you here you have a gas, okay. If you supply the heat energy to the cylinder, the piston move up. So in that case, work is done, we say, by the system. If the work is done by the system, we simply take that positive. If you move the piston downward, okay, then we call work is done on the system. Work is done on the system, that is simply we take as a negative number, okay. So the work done, you need to know that work done. So and you need to know the first law of thermodynamics. You need to know the internal energy. What is internal energy, okay, and of course second law of thermodynamics. Mostly this is the important part in chapter 18, okay. And we talk about, before this chapter in heat and thermodynamics, we talk about the, here in thermodynamics, what we need to know is, we talk about the heat and temperature, we talk about the linear expansion, volume expansion, we talk about the specific heat capacity. So specific heat capacity is kind of important here. Specific heat capacity, we have a specific heat capacity and latent heat. Specific heat capacity is simply C. And do you know what is specific heat capacity? The amount of heat energy required to raise the temperature by 1 degree Celsius. 1 kg object by 1 degree Celsius. Like you have a, let's say, you have a container. Here you have a 1 kg water. 1 kg water at, let's say, at 20 degrees Celsius. Just water, forget about the container, okay. I have 1 kg water at 20 degrees Celsius, room temperature. Now, if you supply the heat energy from here, this is Q is the heat energy. So, amount of heat energy required to raise the temperature of 1 kg object by 1 degree Celsius. That is called as the specific heat capacity. And to calculate the specific heat capacity, you use this formula Q. This is the total heat energy. This is equal to M. M is the mass. Here I use 1 kg, whatever. Okay, M is the mass. C is the specific heat capacity. Delta T is the change in temperature. Here Q, total heat energy. Okay, M, this is mass. Delta T, this is your change in temperature. And this equation Q equal to MC delta T. MC, this delta looks like a AT, so it looks like CAT. Just to memorize, okay? CAT cat. So people, they simply call MCAT equation. Actually it is delta, okay? Don't confuse. So if you have to calculate the specific heat capacity, you have to use this equation Q equal to MC delta T. You already did this. Okay. So from here, if you want to calculate C is the specific heat capacity. This is equal to Q divided by M delta T. Okay. So now if you want to write down the unit of specific heat capacity, now look at this. Q is joule. M is kg. Delta T is the temperature, change in temperature. You can write down Celsius degree or degree Celsius. So this is the specific heat capacity of whatever unit of specific heat capacity. And different object, they have a different specific heat capacity. Different object, they have a different specific heat capacity. So for example, if you would like to know the specific heat capacity of different object, like the water, C, this is the specific heat capacity of like water. It is kind of big number. I think this is 4,183. Different textbooks, they have slightly different number. 4,183 joule per kg Celsius degree. Water has a kind of big specific heat capacity. That is why water takes a long time to heat. Okay, it takes it needs huge amount of energy. If you want to heat the water, it needs like a huge amount of energy. For example, let me give you one example. If you go to the beach, like there is a sand, like you can think, like let us suppose there is water. There is a water here, and here you have a sand. This is a sand. This is here you have a sand here. So if you go to the beach, this is the beach, sand here, water there. Let's say at noon, you go to the beach in summer at noon. If you touch the water is cold. Like let's say at noon or 1 p.m. for example, at 1 p.m. if you touch the water is cold. Now if you touch the sand, sand is really hot. Why? Water has a big specific heat capacity. It takes a long time to heat. That's why water is still cold. But sand, it has a, the specific heat capacity is very low, small. I don't know the number, but I know that the specific heat capacity of sand is smaller than less than the specific heat capacity of water. The specific heat capacity of sand is less, very, very less. So sand heated quickly. That is why at 1 p.m. if you touch the sand is hot, water is cold. Now, at night, like at 10 p.m., if you touch the water is hot. Touch the sand is cold. Why? Because sand has a specific heat capacity less than water. So the rate of cooling of sand, it cool down quickly because its specific heat capacity is less than water. But water takes a long time to cool down. So at 10 p.m. water is still hot, but sand is cold. So different objects, they have a different specific heat capacity. Water has 4183 joule per kg Celsius degree. I think if you want to calculate, know the specific heat capacity of aluminum, I think aluminum has a 900, okay, 900 joule per kg Celsius degree. Please check this number, okay? You can do the Google. Different objects, they have a different specific heat capacity. So you need to know the specific heat capacity equations, okay? Sometimes people, they can ask you. And another thing we talk about is like we talk about the latent heat also. The latent heat equation is Q equal to ml. Q equal to ml. Here L is this is the latent heat. So what is latent heat? We already did it. So the amount of heat energy required to change the state without changing temperature. 0 degrees Celsius ice to 0 degrees Celsius water. Solid to liquid, but you keep the temperature same, 0 degree to 0 degree. So latent heat of, that is latent heat of ice. From ice at 0 degrees Celsius to water at 0 degrees Celsius. You see, ice is solid, water is liquid. Temperature 0 degree, 0 degree. No change in temperature, but what is change? Phase change, solid to liquid. That is what we call the latent heat. And there are two. One is latent heat of fusion of ice, solid to liquid. Another one is 100 degrees Celsius water, 100 degrees Celsius steam. Steam is gaseous state, water is liquid state. 100 degree, 100 degree. So we call that latent heat of vaporization. You have a two, latent heat of fusion of ice, latent heat of vaporization. So we did this already. Okay, so we did this equation also. This is a latent heat equation. Okay, and we also talk about the conduction, convection, radiation. Okay, so please recall that. And I think that's all. Thank you.